linear modeling. But this graph is a bit under misapprehension because a lot of people think that this graph is the starting point of the modeling. If you think that, you will be wrong because this graph is the ending point of a nonlinear model. Indeed, let's assume that we compute x times beta, that on this graph is going to be represented by zeta. As you see, by using a cumulative density function that is a domain between minus infinite and plus infinite, allows me to see that any real value of zeta, I'm going to be okay, because as you can see, the probability, which is here, is always between 0 and 1. And so, by using that kind of cumulative density function, so the standard normal cumulative function, I'm going to be sure that my outcome is going to always be a probability. Let's go on the logic model now. Okay, so the logic model is not really different. It's not far from the probability modeling. At the end of the day, it's pretty much the same stuff, but I want to just to be sure that you get the main point. What do we do in nonlinear models? We just run a regression by using maximum likelihood estimation. We get the estimate for the coefficient, we compute x times beta, and we have this value. We take this value and we plug this value in the cumulative density function, and this function is going to give me my outcome. Well, logic is pretty much is just different about what function the logic model intends to use. Indeed, in the physics world, nothing is impossible. In in physics world, indeed, every event has a probability of occurring. There was one time when there was a famous paper written by Thomson, who was the guy who demonstrated the theory of Hubble on the universe, that say in physics everything is possible. It's still possible that if I smash a dish on the floor, this dish is gonna reconstruct itself. It's a fancy way to say that in physics every event has a probability to occur. Well, it turns out that if the event has a probability of occurring itself, it has to be a odds ratio too, because there is a direct relationship between probability and odds ratio. Indeed, odds is just p out of 1 minus p. And as you can see, there is a strong difference between the odds ratio and the probability of the said event. Indeed, the probability goes from 0 to 1. Under Kolmogorov assumption, the domain of probability has to be 0, 1. However, on the other hand, odds ratio has a different domain. Indeed, odds ratio goes from 0 to infinite. As you can see, there is no sign. It's not our mistake, but if you can see, p equals to 1 means that odds ratio is going to be 1 out of 1 minus 1. So 1 over 0. So I can assign a sign now, but it doesn't matter honestly. Well, it turns out the following concept. If I take the odds of an event, I'm gonna move my domain from the probability world to odds world. However, the odds world is made by domain which is between 0 and infinite. However, I have to be sure that given any real value of zeta, which is equal to x times beta, I'm gonna get a probability. When I state given any real value of zeta, I mean that I have to extend the domain of my variable because I have to be sure that my function is going to work on infinite world to be sure that I cannot go wrong. Go to the next slide. Well, it turns out that I can do that by taking the log of the odds. Indeed, the log odds function has a bigger domain. The first limit and the second limit just describe the domain of the log odds function, and as you can see, taking the log allows me to go from this word to this word. So I'm able to extend my domain, taking a new line that goes from 0 to minus infinite. Next slide. Okay, so how do we act in this case? We run the regression, we get the estimate for the coefficient, we are able to compute x times beta, we take this number, which is my zeta, and apply this number in this function. So, as you can see, these are the processes that end up with this formula. So, taking the log of the odds here, where you, by the linear probability model, you can be said to be a probability. We know that you cannot satisfy the probability properties, but let's assume that u is still a probability here. So let's take the log of the odds here, and let's assume that this log odds is equal to our estimate. by doing some easy mathematical stuff, we can end up with this formula, which is these two. So what we do? We run a regression, we get this beta, we have this x because it's our data set, and we just plug this number into this function. This function is going to give me my outcome, which is going to be always a probability. So you can go to the next slide. So I just overtook the first row back of a linear probability model. Now I'm sure that given any real value of x times beta, I'm gonna always get a probability. However, I need to overcome two drawbacks: the unique marginal effect and the heteroscedasticity. Well, it turns out that in a linear regression here, if the coefficient on x is beta, the first derivative of u over xi is going to be beta I. So what does it mean? That if xi changed by 1 unit, u is going to change by beta I times delta xi. In nonlinear models, we cannot state this kind of stuff because the first derivative here is going to be beta I times this stuff here. This stuff here is just a cumulative density function that takes a value, and this value depends on the other regressor. So if we want to compute the first derivative of x1, this guy is going to be beta 1 times this function that depends on what values I selected for the other regressors. So since I have n regressors, and since numbers are infinite, so I can select for my regressors infinite numbers, this first derivative is not going to have a limit because there are going to be infinite first derivative since I can choose every value I want for the other regressors. So the nonlinear models are able to do something more than the linear modeling because the first derivative is not just unique. So as the example of Basilio, if we run a linear probability model and we want to understand if having one son more is something bad for me, something worse for the first or two, well, in the linear probability model we cannot do that because having one son is going to have the same impact of being the labor force as having two sons because the marginal effect is 1. In nonlinear model I can allow for some degrees of freedom for. Let's go on my last slide. Well, I just need to solve